All right, hello. So I have a request for exercise 7.4, and so let's take a look, and bear with me, this one's a longer one, so it might take me a little longer to get it set up. But the basic idea is we're trying to solve for the composition of the azeotrope in our binary system. And so when we have an azeotrope, alpha is going to be equal to 1. Okay, so this essentially is going to be my error function. I'm solving for when this is equal to 1. All right, so my error function will be 1 minus this. So I'm trying to solve for the composition. Okay, so we're given the temperature. We're told the temperature is 25 degrees C. Okay, so these two terms here, these are just our pure component vapor pressures, which are given by Antoine equation. And so we're given parameters A, B, and C, Antoine constants. So those are only a function of T. So knowing T, we should be able to directly calculate P1 sat and P2 sat. Right, essentially just be 10 raised to this. And then here we have this ratio of gammas, activity coefficients of component 1 and 2. So again, temperature is known, right? And so when we measure or model excess Gibbs-free energies of liquid phases, typically ignore pressure dependence. Okay, and so what's key is these are only a function of temperature and composition. Since temperature is fixed, they're only a function of composition. All right, and so those are going to be described by this Van Laar equation here, which doesn't even explicitly contain temperature. All right, it just contains composition, where we're provided with values of these constants, these parameters A12 and A21. Okay, so if I look back at this equation, right, the only unknown is going to be x. All right, so my error function is going to be 1 minus this, right, and I'm going to end up using F0 to keep iterating on values of x until that expression is equal to 0. Okay, so let's go and take a look at the code I received. Okay, here we go. Okay, let me shrink my head up a little bit. You don't need to see me anyways, right? All right. So let's see here. So x1's an input. Okay, so I know that's not going to be right. That's what I'm trying to solve for. So let's just go ahead and, since I know I'm going to get rid of that, okay, it's a good idea to make x2 1 minus x1. Okay, but let's move on. So AW, BW, CW, AB, BB, and CB, okay, those should be my Antoine constants for water and butanol. Okay, good. Here's my constants for my Van Laar equation. There's my temperature. That's good. And then what it looks like I'm doing here, okay, let's try and maximize this so it becomes easier to see. What I'm trying to do here, it looks like, is I have an error function for my two Antoine equations, right? Log base 10. My pressure is equal to A minus B over T plus C. And then I'm using F0 to solve for P. So you could do that. That's correct. You could use that to solve for P. There's nothing wrong with that. But in theory, it's not entirely necessary. Okay, so let's go and update this. So let's add some labels. So here's my Antoine constants then for water. Here's my Antoine constants for 1-butanol. Okay. Now I'm just going to add at the top a single temperature, so keep track of these things. So temperature in C. So, and then if I use this capital C notation, TC is 25. Okay. The one thing I'm going to want to check on though is what units of temperature does my Antoine equation use? It uses temperature in C. Okay, so we're good. Okay, so use temperature in C there. Have my Antoine constants for water, Antoine constants for butanol. Okay, so I'm just going to use a constant temperature here. And then let's say caps. Compute vapor pressure of water in millimeters of mercury. Okay, now I'm pretty sure the units are millimeters of mercury. Okay, it doesn't really matter though, because I'm going to have a ratio of pressures here. Okay, so it'd be in millimeters of mercury. Okay, if I were to copy and paste this, okay, or cut and paste that, okay, this is okay in theory. Okay, I would have to change this to TC, but it is a little overkill, right? So essentially what this would do is it would pass my Antoine constants and the temperature to this helper function, this air function. Okay, this just says I need to do that. And then this just says that's using T. And then it would, F0 would solve for PW. Okay, and so you could do that. But I would say it's not really necessary, because this one's easy enough to solve, right? I can just do P underscore W is 10 raised to that. A minus B divided by T plus C would give me log base 10 of the vapor pressure, so I just do 10 raised to that to get pressure. Okay, so I'm going to do that only because it makes the code easier. All right, and so I'll clear this guy out. Okay, and then we'll repeat for water, or for butanol. So we'll compute vapor pressure of 1 butanol in millimeters of mercury. Okay, so come down here again, we had the same thing, and there's nothing wrong with it. But again, this one's easy enough to solve analytically, so I'm going to solve it analytically. Okay, so P underscore B is equal to 10 raised to that. Okay, and it's T underscore C. Okay, cool. Okay, I'm going to click save. Okay, so now I have my 2 vapor pressures computed. Okay, next would be, if I look at the problem, these gammas, right? Now these gammas are going to be a function of x. Okay, so what's going to happen is I'm going to have to calculate those gammas within my air function. Okay, so let's go to see what we have in terms of air function. Right, so we can delete those. We can delete this. Okay, let's see what we have here. So here's these are expressions for log gamma 1 and log gamma 2. Okay, and I'm going to work with these since presumably they're right. I'll just have to update those function signatures. Okay, so what I'm going to do though is I'm going to create a new function. Res is let's call this azeotrope finder. Okay, now I'm solving for x1. Okay, but then as I type up this air function, I'll also get an idea of all the parameters that I need to pass. All right, because if I just try and translate the air function from the text, it'd be 1 minus. Okay, they'll use this y1, y2 notation for gamma 1 and gamma 2. It'd be y1, say, divided by y2. Okay, and that'll be times, let's do P1 divided by P2. Okay, so got it. Okay, and component 1 is water. Okay, so now let's tidy this up and figure out exactly what we need. Okay, so if I look at my air function, okay, I'm going to need the vapor pressure of water and butanol, which I computed up here. Okay, so I'm going to add to my signature PB. Okay, or PW and PB. All right, I'm going to try and use the same notation as up above. PW and PB. Okay. Again, component 1 is water. Just trying to make sure I got those before we trudge forward. Okay. Now I'll also need gamma 1 and gamma 2. Okay. So here we have functions for this. Okay. So res was okay, so this will give me log gamma 1. Okay, got it. So this is going to need knowledge of A12 and A21, which I've defined up here. Okay, so I can calculate log Y1, okay, and that will be, actually, instead of setting this up in their function, so log Y1 is this. Okay, so you use x2, so let me do x2 is 1 minus x1. Okay, and let's type this up and then we'll kind of make sense of it. Okay, so log gamma 1 would be, okay, y1's not going to be an input here. Since I'm not going to be using F0 to solve for it, I'll just keep x1, A12, and A21, right? Because it looked like you have F0 calls up here, and you could do that, but again, it's kind of overkill since F0 is going to keep guessing values of x1 as I try and solve this error function, and for each guess of x1, it can just directly calculate gamma 1. So there's really no need to set up an F0 call to solve for gamma 1. Just directly calculate it. Okay, so x2 is 1 minus x1. Okay, let me tab this in. So this is going to have inputs of x1, then my constants for Van Laar. X2 is going to be 1 minus x1, and then this is going to return, and this is going to be log gamma y1. Okay, so this is essentially a function to compute ln of gamma 1. Okay, so ln gamma 1 will be this function y1, which takes as an input, up here I have x1, let's do x underscore 1, be consistent, x1, comma, a12, comma, a21. So I have that. Okay, now we're going to need log gamma, and then y1 would be exponential of log y1. Okay, got that. And then let's do the same thing here. Okay, so this will be for gamma 2. Okay, I'm going to make the signature the same. So x1, and then my Van Laar parameters. Okay, if I need x2 for the calculation, I'll just say x2 is 1 minus x1. Okay, and so rather than calculating, say, x2 up top and passing, you have to find this easier since they are related so simply. Okay, so this would give us log gamma 2. Okay, again, I'm assuming this is correct. I haven't checked this. So this is partially vectorized, but not completely. And we could go back and take a look at that if we wanted. Oh, okay. So one thing I noticed here is this is called y1, and then I don't know if there's going to be an issue with that being a function in variable. Okay, so what I'll do is let me just use G1s for gamma 1s. Okay, it's not the best notation, but just in the interest of getting this cleaned up right here, I'm going to give that a try. And then that way that underlining goes away. Alright, so as we trudge along then, so ln y2 would be y2, okay, and I'll give x1 a12, a21, okay, then g2 would be the exponential of ln y2, okay, so I'm going to compute gamma 1, compute gamma 2, and then here's my air function. Yeah, okay. Now, if I come up here then, let's see. So I'm going to use F0 to solve for x1, so I need to get those additional parameters to it. Okay, and so kind of essentially the same notation. Okay, so you have all the right notation, it's just kind of piecing these different pieces together. So we'll do so I always do this like reduce, because all I'm doing when I'm defining these anonymous functions is passing parameters to it. Okay, so the final input variable I want this guy to have that I can use with F0 is just x1, and then when I pass that value of x1, I'm just going to call azeotrope finder, and since I use the same variable names as I did up here, down here, you can just copy and paste it, right? And so that's where being consistent can help out sometimes. And then all that's left is to solve. Let's see. So we're using res, so res would be F0. Okay, now that I've defined this anonymous function, I don't need the at in there because it's already a type function handle. Now I can't search completely over the range 0 to 1, right, which would be the applicable range of compositions. So I need a number slightly greater than 0 and a number slightly less than 1. So I'll do, well, there's a number of ways you could do it. One could be, I define some variable, call it like tiny, and tiny is 1e to the negative 10. So then my range could be 0 plus tiny to 0 minus tiny. All right, where it's just some number close to 0, so that if I want to create bounds that are just above 0 and just below 1, right, I could just use tiny essentially to do that. Okay, so let's give this a try, see if it works. Nothing's highlighted right now, and then we can kind of walk through it. Okay, so I need to move my head so I can restore the screen. Okay. Oh, well, now I got a big head. We do not want that. Yeah. Bam. All right. So now if I were to run this, this is just homework 7.4. Okay. Maybe I want to store the output to x1, and I get 0.7940. Hey, 0.7940. We got the answer. Okay. But now let's kind of walk through this just to make sure we have a complete handle of what we have. Okay, so I have a function with no inputs. And so I like functions with no inputs as compared to scripts, because then that workspace is protected. So I prevent having name collisions and things like that. Okay, and so my strategy then was, so I specify the temperature, and then here's my Antoine constants for water. Then once I have those, I can just use my Antoine equation to directly solve for temperature. So in the original version of the code, you had it set up so that you had a air function that was log base 10 of pressure minus the right hand side of the Antoine equation, and then you could do that, and so then F0 could solve for pressure so that the equation's satisfied, but it's just as easy to solve this one directly. Okay, then I repeat for butanol. Okay, and so I have my ratio of vapor pressures then, right? So I have this. Okay. When it comes to the ratio of gammas, there it's problematic because they're functions of x's. Okay, and so then the strategy would be, okay, let me go and look at what my air function would be. So if I look at my air function, okay, I have my vapor pressures; those I know, but then I'm going to have to calculate these gammas. And so how gamma will proceed is, I know I'll use F0 to systematically iterate on values of x until it finds the x value, so that my air function is satisfied. Okay, so that my air function returns a value of 0. So every time F0 guesses a new value of x, well then I have x, so I can directly calculate gamma. Okay, and so then what I did is, you had these nice functions to calculate log gamma 1 and log gamma 2, and I like this because these equations can get very big and ugly fast. And so calculate gamma 1 and gamma 2, right? And this has to occur, right? So originally it was in the top function. This has to occur in my air function because they're functions of composition. and I'm trying to find the composition for which this equation is satisfied. All right, and so these are in my error function, because then F0 will keep guessing values of x1 until this equation is satisfied. Okay. Then one issue or subtlety is here I use kept with y1 the name of your function. So then in terms of a variable name to store gamma 1 and gamma 2, I change it to g since it didn't look like the function. But so this occurs within the error function. Then I calculate alpha minus ratio of gamma times ratio of pressures. And then essentially we just use F0 to keep iterating on this, right? Iterating on x1 until it's satisfied. So I have the Van Laar constants up here. Just as well could have defined them in the anonymous function. Doesn't matter. In the same token, I calculate vapor pressures up here. All right, you just as well could have put that in the error function, right? Doesn't really make a difference. Okay. My personal preference is to try and keep as much as possible up in the top function. Only because if I wanted to modify this for a new problem, so now say I had another binary system and I had Van Laar constants and a new set of Antoine constants, right? I just update this material up top and rerun, right? That way I'm not searching through the code, right? So it's just a personal preference. I prefer to put everything in the top and then just use anonymous functions to pass things down, right? And so azeotrope finder needed the vapor pressures and Van Laar constants, which are defined up top. And so I pass those via an anonymous function and then use F0 to solve. Right? And so then in the helper, I don't define any constants. They're just, my equations. And even this is kind of cool how you had the Van Laar calculation separated. So if you wanted to solve the same problem, but maybe you were using a different model for my gammas, you just have to say update these. So if I had N or TL parameters, all I would need to do is update that small piece of my code and get that running again. Okay, so there you go. That was problem 7.4.